Imagine a world connected not by heavy copper wires or clunky mechanical switches, but by slender, almost invisible threads of glass channels that carry pulses of light and ferry information at incredible speeds. This is not science fiction, but the foundation of our modern fiber optic networks. To appreciate the marvel of fiber optics, we must first consider the very nature of light itself and the subtle interplay of simple physical principles that allow it to race, unimpeded, down these transparent highways. Light, as we encounter it every day, seems straightforward: a beam from a flashlight, the warm glow of the sun, the gentle illumination of a screen. But at its core, light is both a wave and a particle, a duality that has intrigued scientists for centuries. For fiber optics, it is the wave-like behavior of light that takes center stage, especially how it behaves when moving from one material to another. This phenomenon, known as refraction, is at the heart of how fiber optics work. Refraction occurs when a light wave changes speed as it passes from one medium to another, say, from air into glass or from water into plastic. Each material affects the speed of light differently, a property described by its refractive index. The higher the refractive index, the slower light travels through that material. When light encounters a boundary between two materials with different refractive indices, its path bends. This bending is not random, but governed by a precise mathematical relationship known as Snell's law, which tells us how much the light will bend depending on the angle at which it hits the boundary and the refractive indices of the two materials involved. To see this principle in action, think of a straw in a glass of water. The straw appears to bend at the surface, a visual cue of refraction at work. In fiber optics, this effect is harnessed with far greater precision. The core of an optical fiber, a slender thread of glass or plastic, has a higher refractive index than the surrounding material, known as the cladding. This difference, though minuscule, is the key to keeping light trapped within the core, guiding it along a winding path that can stretch for kilometers. But refraction alone cannot confine light over such great distances. If light simply refracted at the interface between the core and the cladding, much of it would leak away, dispersing into the surrounding environment. The true magic of fiber optics comes from another, more dramatic phenomenon: total internal reflection. Total internal reflection is a special case of refraction. When light traveling inside the core hits the boundary with the cladding at a sufficiently shallow angle, it is not refracted out, but instead bounces back entirely into the core, as if the boundary were a perfect mirror. This does not happen at all angles. There is a critical threshold, the aptly named critical angle, beyond which the light is completely reflected rather than escaping into the cladding. The critical angle depends on the refractive indices of both the core and the cladding. Only when the light strikes the boundary at an angle greater than this critical angle does total internal reflection occur. This principle is not a mere accident. It is the essential feature that allows optical fibers to act as waveguides for light. The core always has a higher refractive index than the cladding, ensuring that, for a wide range of incident angles, light remains trapped inside. Whenever a light ray traveling through the core encounters the interface with the cladding at an angle steeper than the critical angle, it is bounced back, time and again, zigzagging its way down the length of the fiber. At these angles, there is no transmission of light into the cladding, only reflection, allowing the light to travel vast distances with astonishingly little loss. The concept of total internal reflection is not new. It was first explored in the 19th century. In the early 1840s, researchers like Colladon and Babinet in Paris demonstrated the principle of light guidance by refraction, laying the groundwork for what would become fiber optics. Later, in the mid-19th century, John Tyndall famously showed that light could be conducted along a curved stream of water, a vivid demonstration of total internal reflection in action. But it would take more than a century before these concepts were refined into the slender, flexible fibers that underpin today's communication networks. The structure of an optical fiber is both elegant and purposeful. At its heart is the core, usually made of highly purified glass, though sometimes plastic is used for specialized applications. This core is surrounded by the cladding, a second layer of glass or plastic with a slightly lower refractive index. The refractive index difference, often less than a fraction of a percent, is meticulously engineered to ensure optimal light guidance. This arrangement forms a waveguide, a structure that channels light by repeatedly reflecting it at the core cladding boundary. Optical fibers come in several varieties, but the first widely used design was the step index fiber. In step index fibers, the refractive index changes abruptly at the boundary between core and cladding, hence the name. Light entering the core is guided in a series of discrete reflections, much like a bouncy ball ricocheting down a hallway. While step-index multimode fibers were the earliest, today most high-performance communications use more advanced designs, though step-index fibers still have roles in certain plastic optical fiber and specialty applications. The efficiency of light guidance in an optical fiber is described by a parameter known as the numerical aperture. The numerical aperture is determined by the difference in refractive indices between the core and the cladding and defines the range of angles at which light can enter the fiber and still be guided by total internal reflection. A higher numerical aperture means the fiber can accept light over a wider range of angles, making it easier to couple light into the fiber. However, for long-distance, high-speed data transmission, precision and control are paramount, so the exact values are carefully dictated by international standards such as International Telecommunication Union, Telecommunication Standardization Sector G 652 and G 6757, as well as International Electrotechnical Commission 60793, which specify the required refractive index differences and geometric tolerances for fibers used in telecommunications. The result of all this careful engineering is a cable that can carry pulses of light, each representing bits of data across continents and under oceans. Light is launched into the fiber, bouncing along the core, confined by total internal reflection, with minimal loss even over distances of many kilometers. This stands in stark contrast to traditional copper wires, where electrical signals degrade much more rapidly, limiting both distance and data capacity. Fiber optics outperform copper not only in bandwidth, the sheer volume of information that can be transmitted, but also in preserving the integrity of the signal over long hauls. The journey from theory to practical fiber optics was not without obstacles. In the middle of the 20th century, researchers recognized that impurities in glass were the primary cause of light loss, or attenuation, within fibers. The breakthrough came in the 1960s when Charles K. Howe and George Hockham demonstrated that, with sufficiently pure glass, light could be transmitted over long distances with manageable losses. Their insight and subsequent research paved the way for the development of optical fibers that could be used for real-world communications. This advance, which focused on reducing loss due to material imperfections, was a turning point, allowing fiber optics to evolve from laboratory curiosities into the backbone of global communications. The adoption of fiber optics gained momentum in the decades that followed. The first commercial fiber optic communication system was installed in Chicago in 1976, marking the beginning of an era in which information could be sent at the speed of light, unburdened by the limitations of metal wires. Today, the reach of fiber optics extends far beyond communications. They are used in lighting, medicine, inspection, and sensors, anywhere the precise, efficient transmission of light is needed. At the heart of every fiber optic system, from the simplest medical sensor to the vast networks that link continents, are the principles of refraction and total internal reflection. These concepts, elegant in their simplicity and profound in their consequences, allow us to guide light with incredible precision. The core must always have a higher refractive index than the cladding, ensuring that the critical angle for total internal reflection is maintained. Only under these conditions does the light remain confined, skipping along the inside of the fiber for kilometer after kilometer, carrying with it the information that powers our connected world. As we peer into a glowing strand of fiber, we witness a dance of physics, a choreography dictated by the laws of light and material. Each pulse that races through the core is guided by boundaries invisible to the naked eye, yet perfectly engineered to keep the signal on course. The sparkle of a diamond, the bend of a straw in water, the rainbow on a soap bubble, all are everyday reminders of these same principles. But in fiber optics, these effects are not just curiosities, they are harnessed, refined, and put to work, forming the very foundation of our digital age. This is the essence of fiber optics, a profound interplay between the nature of light and the ingenuity of human engineering. The chapters that follow will build upon these foundations, exploring how these slender fibers are manufactured, deployed, and put to work in the service of communication, innovation, and discovery. But at their core, all fiber optic technologies rest on these bedrock principles: refraction and total internal reflection. Simple ideas that have enabled a revolution in the way we share, connect, and understand our world. To understand the marvel of fiber optics, imagine the journey of a single pulse of light as it speeds through a strand thinner than a human hair. This remarkable journey is made possible by the ingenious structure and materials that form an optical fiber. At its core lies a slender filament of glass or plastic, so pure that even the tiniest impurities could impair its performance. This core acts as the main highway for light, and its exceptional purity and transparency are essential for transmitting information across vast distances. Surrounding the core is the cladding, a sheath made from a material similar to the core but with a slightly lower refractive index. This subtle difference keeps the light locked inside the core, ensuring the signal does not leak away but instead travels faithfully from sender to receiver. Protecting these inner layers is the coating, a flexible material that shields the delicate glass or plastic from scratches, moisture, and other environmental hazards. But the journey does not end there. To withstand the rigors of installation and daily use, fiber optic cables include strength members, often made from materials like Kevlar, that give the cable mechanical resilience, preventing it from snapping or stretching under tension. Finally, the entire assembly is wrapped in an outer jacket, a tough exterior that guards against the elements, from rain and sunlight to chemicals and abrasion. While the basic anatomy remains consistent, the exact materials and dimensions can vary depending on the application. Most often, the core is crafted from highly purified glass, specifically silica, chosen for its transparency and low loss at the wavelengths used in telecommunications. In certain cases, such as short-run or specialty applications, the core may be made from plastic, offering flexibility and cost savings where absolute performance is not as critical. The cladding, typically made from doped silica or another type of glass, is engineered to have a lower refractive index than the core. A subtle but essential distinction. It is this precision in engineering, getting the refractive indices just right, that makes high-performance fiber possible. Beyond the core and cladding, the coating is usually a polymer, applied in multiple layers for added protection. These coatings do not affect the passage of light, but are vital for maintaining the integrity of the fiber during handling and installation. The strength members are chosen based on the cable's intended use. For cables that might be pulled through conduits or suspended between poles, Kevlar or similar materials provide the necessary toughness. The outer jacket is tailored to the environment, sometimes ruggedized for outdoor use, sometimes flame retardant for indoor settings. Within this carefully constructed environment, pulses of light are sent down the core, carrying information encoded in rapid bursts. The light source, often a laser diode or light-emitting diode, LED, injects photons into the fiber. As these photons travel down the core, they encounter the boundary with the cladding. Thanks to the difference in refractive indices, each photon is reflected back into the core rather than escaping, even as the fiber bends and twists along its path. This mechanism, known as total internal reflection, keeps the light tightly guided, allowing the signal to reach its destination with remarkable fidelity. But not all fibers are created equal. The world of optical fibers is divided into two principal types, single-mode and multi-mode. The distinction between them lies in how they manage the passage of light, which in turn shapes their performance in applications. Single-mode fibers have an extraordinarily small core, typically less than 10 micrometers in diameter. This narrow pathway allows only a single mode or path of light to propagate. The result is minimal distortion and the ability to carry signals over long distances without significant loss. This makes single-mode fiber the backbone of long-haul telecommunications, spanning continents, linking cities, and supporting the Internet's global reach. However, this precision comes at a cost. Single-mode transceivers, which inject and receive these signals, are typically more expensive than their multi-mode counterparts, and installation requires meticulous alignment. Multi-mode fibers, by contrast, feature cores that are much wider, often 50 or 62.5 micrometers in diameter. This generous space allows multiple paths, or modes, of light to travel simultaneously. Each mode takes a slightly different route, bouncing off the cladding at various angles, which makes the fiber easier to connect and more forgiving to install. Multi-mode fibers are thus favored in environments where distances are shorter and the demands of installation are more practical than technical. Think data centers, office buildings, and campus networks. Multi-mode systems are generally more cost-effective for these scenarios, as the transceivers are less expensive and the fibers easier to handle. The choice between single-mode and multi-mode fibers is not just a matter of core size. It involves careful consideration of distance, bandwidth, and cost. Single-mode fibers, with their tiny cores, excel at transmitting data across tens or even hundreds of kilometers, making them indispensable for telecommunications and high-speed data links. Multi-mode fibers, with their broader cores, are limited to shorter distances, usually up to a few kilometers at most, because the multiple modes tend to arrive at slightly different times, a phenomenon known as modal dispersion. This causes the light pulses to spread out and can blur the signal if the fiber is too long. Within multi-mode fibers, there are further distinctions. Some are constructed as step-index fibers, where the refractive index changes abruptly at the core cladding boundary, while others are graded index fibers, in which the refractive index decreases gradually from the center of the core outward. This grading helps synchronize the arrival times of the different modes by making the paths more uniform, reducing the blurring effect and improving performance over longer distances. The performance of an optical fiber is often measured by two key factors: attenuation and dispersion. Attenuation refers to the gradual loss of signal strength as the light travels through the fiber, typically measured in decibels per kilometer. This loss can have both intrinsic and extrinsic causes. Intrinsic attenuation comes from the material itself, absorption of light by the glass, or scattering of photons by microscopic fluctuations in the material's density. Rayleigh scattering, in particular, is a significant contributor caused by tiny variations in the structure of the glass. Extrinsic attenuation arises from imperfections or mishandling, macrobends, where the fiber is bent too sharply, and microbends, which are tiny distortions along the fiber's length, can both scatter light out of the core. Dispersion, the other major factor, is the spreading of light pulses as they travel through the fiber. There are several kinds of dispersion, but modal dispersion is most relevant in multi-mode fibers where different paths cause pulses to arrive at different times. In single-mode fibers, chromatic dispersion, caused by different wavelengths of light traveling at slightly different speeds, becomes more significant, particularly at high data rates. Both attenuation and dispersion limit the distance a signal can travel before it needs to be regenerated or amplified. The materials used in fiber construction have a substantial impact on both attenuation and dispersion. The pursuit of ultra-pure glass has been a driving force in fiber optics, and today's fibers are made from silica so pure that impurities are measured in parts per billion. Plastic fibers, while less capable over long distances, offer advantages in cost and flexibility for specific uses. The cladding, though similar in composition, is engineered for its optical properties rather than absolute purity, ensuring the right balance between performance and manufacturability. The quality of the fiber itself is only part of the equation. The entire system's performance also depends on the light source, the connectors joining fibers together, and the environment in which the cable is installed. For example, the type of light source can affect how well information is transmitted. Lasers provide tightly focused beams ideal for single-mode fibers, while LEDs are commonly used with multi-mode fibers. Connectors must be precisely aligned to avoid loss at the junctions between fibers. Environmental factors, such as temperature swings, humidity, vibration, and exposure to electromagnetic interference, can all impact performance. Even the length of the fiber and the rate at which data is sent play a role. Greater lengths and higher speeds can exacerbate attenuation and dispersion, requiring more careful engineering. All told, the construction and function of optical fibers represent a delicate balance of materials, science, physics, and practical engineering. Each layer, each choice of material, and every design decision is driven by the need to transmit light efficiently, reliably, and over the required distance. International standards have arisen to guide the manufacture and deployment of these fibers, ensuring that single-mode and multi-mode fibers can be used interchangeably across systems and continents. For instance, standards like ITU, TGG, 6F52 define the characteristics of single-mode fibers, while standards such as ISO/IEC 11801 provide specifications for multi-mode fibers. As fiber optics has evolved, the range of available cables has expanded. Today, fibers are not only classified by mode single or multi, but also by their construction, performance, and intended application. Some are ruggedized for outdoor use, others are designed for tight bends in cramped spaces, and still others are optimized for the highest possible data rates. But at their core, all optical fibers share a common ancestry, a slender thread of glass or plastic, meticulously engineered to guide light from one place to another. Fiber optics has redefined what is possible in communication and sensing, allowing humanity to send information farther, faster, and more securely than ever before. The anatomy of an optical fiber may seem simple, but it is the result of decades of innovation and refinement, a testament to what can be achieved when science and engineering work in harmony. As we continue to demand more speed, greater capacity, and new forms of connectivity, the humble optical fiber will remain at the center of our digital world, quietly and efficiently guiding pulses of light along their invisible paths. Fiber optics have become the invisible threads that bind the modern world, their reach and versatility extending far beyond what even their earliest pioneers could have imagined. For most people, the mention of fiber optics brings to mind blazing internet speeds and crystal-clear phone calls. But these slender filaments of glass and plastic, thinner than a human hair, have woven themselves into industries as diverse as medicine, energy, and manufacturing. Their story is one of relentless improvement and adaptation, a testament to the power of light harnessed and guided with extraordinary precision. The most visible, and perhaps most transformative use of fiber optics remains in telecommunications. Here, the promise of optical fibers is realized daily as pulses of infrared or visible light carry vast quantities of data, crisscrossing countries, continents, and oceans. Fiber superiority over copper wires is undisputed, especially where high bandwidth and long distances are needed, or where electromagnetic interference is a concern. These qualities have made optical fibers the backbone of telephone networks, high-speed internet, and cable television, quietly supporting the staggering demands of modern digital life. As households and businesses accumulate ever more connected devices, on average, 17 per United States household, more than double the number less than a decade ago, the capacity and reliability of fiber optics have become indispensable. The numbers tell an extraordinary story. The global fiber network, just considering the cable infrastructure, is valued between $125 billion and $250 billion each year. In the United States, fiber optic access is rapidly expanding. As of June 2023, 55.6% of United States households were within reach of fiber, a figure that rose to 56.5% by 2024 and is expected to approach 80% by 2028. This ongoing deployment responds to soaring demand for bandwidth and speed, driven not only by streaming and remote work, but also by the proliferation of smart home devices, cloud computing, and the rise of artificial intelligence. Telecommunications providers are pushing fiber deeper into their networks, now offering individual homes and businesses astonishingly fast, symmetrical connections, up to 50 gigabits per second. Globally, the scale is even more impressive. The total length of fiber optic cable installed worldwide exceeds 5 billion kilometers, enough to circle the Earth more than 125,000 times. The Asia-Pacific region, especially China, leads in deployment, and the global fiber optics market is projected to grow from $3.2 billion in 2024 to $6.8 billion in 2029, with a projected compound annual growth rate of 16.4%. This is not just a story of technology, but also of infrastructure investment and strategic planning, with governments and private entities alike recognizing fiber as a future-proof asset. Yet fiber's impact extends far beyond carrying YouTube videos or business emails. In medicine, fiber optics have quietly unlocked new frontiers in diagnosis and treatment. Their small size, flexibility, and immunity to electromagnetic interference make them uniquely suited for use inside the human body. Physicians rely on fiber optics for minimally invasive procedures, guiding tiny cameras and instruments deep into tissues through slender catheters, endoscopes, and even forceps. The result is less trauma, faster recovery times, and more precise interventions. High-resolution imaging through fiber bundles allows doctors to see inside the body without large incisions, and real-time monitoring of vital parameters such as pressure, temperature, and blood oxygenation can be performed with remarkable accuracy. In laser surgeries, fiber optics safely deliver energy to targeted tissues, reducing collateral damage and improving patient outcomes. Recent advancements in medical fiber optics have only expanded these possibilities. Both single-mode and multi-mode fibers are used in devices that must meet stringent international standards, such as International Telecommunication Union Telecommunication Standardization Sector, G652, and International Organization for Standardization/International Electrotechnical Commission, 11801, ensuring safety, reliability, and compatibility. Sophisticated sensors built on optical fibers can now measure not only physical quantities like pressure and position, but also chemical signatures within the body, such as blood gases. Remote spectrophotometry, enabled by fiber delivery of light to and from tissues, allows clinicians to analyze biological samples in real time. These advances are supported by the same principles that make fiber optics so valuable in communications, namely their sensitivity, biocompatibility, and resistance to interference. Looking ahead, the miniaturization of fiber optic sensors promises even more portable and powerful diagnostic tools, opening doors to entirely new medical applications. The utility sector has also embraced fiber optics, leveraging their resilience and high capacity to monitor and manage large, complex networks. Utilities depend on fiber for grid management and robust internal communications, particularly in environments where electromagnetic interference from high-voltage equipment rules out traditional copper cabling. Fiber's immunity to such interference ensures that critical control signals and data flow without interruption or corruption. The evolution in this field has been dramatic. where the earliest fiber optic networks transmitted at a modest 145 megabits per second, current systems can achieve speeds up to 13.5 terabits per second. This leap in capacity enables real-time monitoring and rapid response to changing conditions across sprawling infrastructure, enhancing reliability and efficiency. Industrial environments present their own set of challenges: harsh conditions, electromagnetic noise, and the need for precise, real-time data. Here, fiber optics excel in tasks ranging from process control to equipment monitoring. In manufacturing, optical fibers are embedded in machinery to sense temperature changes, detect vibrations, or monitor the integrity of components. Their ability to transmit signals over long distances without degradation and without risk of sparks or interference makes them invaluable in settings where safety and reliability are paramount. Fiber-based sensors are also used in transportation and civil engineering, monitoring the health of bridges, tunnels, and railways with a level of sensitivity that traditional sensors cannot match. Recent technological breakthroughs have further enhanced the performance and versatility of fiber optics. Ultra-low loss fibers, for instance, have dramatically reduced signal degradation over great distances, supporting the expansion of rural broadband and enabling direct connections between data centers and remote communities. These ultra-low loss fibers are instrumental in the rollout of fifth-generation mobile networks, where high capacity and low latency are essential, and in global data transmission, where undersea cables span continents. Bend-insensitive fibers represent another advance, allowing cables to be installed in tight spaces and around corners without compromising signal quality, a crucial benefit in dense urban areas and crowded wiring closets. The process of joining fiber optic cables, once a delicate and time-consuming task, has also seen significant improvement. Modern fiber splicing techniques allow for seamless, durable connections with minimal signal loss, facilitating faster deployment and greater network reliability. These advancements help meet the explosive growth in demand for bandwidth, especially in data centers where the rise of cloud computing, artificial intelligence, and machine learning has multiplied the number of required optical connections 2 to 3 times over. To address bandwidth bottlenecks, researchers are developing multi-core fibers, which pack multiple light-guiding cores into a single strand, dramatically increasing the amount of data that can be transmitted without expanding the physical footprint of the cable. As the fiber optic landscape evolves, new trends are reshaping how networks are planned, built, and managed. More efficient deployment techniques have accelerated the pace at which fiber reaches homes and businesses, and artificial intelligence is now being used to optimize network design and predict maintenance needs. Open access networks, where multiple service providers share the same underlying fiber infrastructure, are gaining traction, increasing consumer choice and fostering competition. Federal funding is driving the build-out of rural broadband, aiming to close the connectivity gap and ensure that even remote communities can access high-speed internet. Despite these advances, the industry faces its own set of challenges. Growth in the telecommunications sector is slowing in some regions, and operators are under pressure to contain costs and adapt to increased competition. The focus is shifting toward business-to-business and government projects, cloud services, and support for the expanding ecosystem of Internet of Things devices and smart city solutions. Meanwhile, the average monthly bandwidth consumption continues to climb, having more than doubled over the past 5 years, and the need for ever greater speeds and reliability is unrelenting. Fiber optics are also being called upon to support new forms of economic activity. Investment in artificial intelligence infrastructure is transforming the economics of telecom, prompting providers to seek new ways to monetize connectivity and reinvent their business models. The trend toward open access and shared infrastructure reflects a broader shift in thinking, where the emphasis is on flexibility, scalability, and resilience. Looking to the future, the potential of fiber optics seems limited less by the technology itself and more by the ingenuity with which it is applied. By 2025, advances in miniaturization are expected to yield portable, high-performance fiber optic sensors that could unlock new applications. The ongoing development of multi-core and specialty fibers will continue to push the boundaries of data transmission and sensing. At the same time, the physical deployment of fiber digging trenches, stringing cables, connecting homes remains a massive logistical challenge, one that is being addressed through a combination of policy, funding, and innovation. Challenges remain, of course. The cost and complexity of deployment, especially in rural or densely populated areas, can be daunting. Ensuring that new networks are compatible with existing infrastructure requires careful planning and adherence to international standards. And as the number of fiber-connected devices multiplies, issues of security, maintenance, and longevity become ever more important. Yet for all these hurdles, fiber optics remain a uniquely future-proof technology. Their fundamental attributes, speed, capacity, reliability, and immunity to interference, make them ideally suited to the demands of the digital age and beyond. Whether enabling a surgeon to look inside the human body, a utility operator to monitor the power grid, or a rural student to join an online classroom, fiber optics have become the quiet enablers of progress. Their story is still being written, one pulse of light at a time, as new applications and advancements continue to emerge from the interplay of science, engineering, and human ambition.